So what I want to talk about is different ways that UEFI firmware ends up on boards. And this seems like a strange thing to present to a room full of people that write firmware for a living, but I want to make sure that there's an understanding of the different kind of ways that you're going to see firmware on boards, not just on the traditional boards, products that you buy at retail, but how you may see it on different development boards or test vehicles that come out. So there is a standard firmware model. This is one I'm quite familiar with because before I worked at Intel, I worked at American Megatrends and did a lot of work on BIOS and UEFI. But there are some different ways that companies are producing and distributing firmware. And again, these options are all based on Intel boards. I know that ARM and AMD and different companies have distribution models for their boards, and some of them may be similar, but I'm not an expert on their methods. So this is going to be presented from the Intel perspective, and there should be some overlap with the way that you see these coming from different companies. And again, most of this is so that people in the room who are OS developers, driver developers, have an understanding of when you pick up a board, if it's development or open source or reference, where did that firmware come from? I.e., who do you blame for problems? Sometimes it's me, most of the time it's not. Okay, so on Intel architecture, we typically have relationships with a original equipment manufacturer, OEM, or the original design manufacturer, the ODM, that is working with a BIOS vendor that's going to produce firmware for a board they're going to ship into retail production. This means that they're going to a BIOS vendor and saying, I would like to license your code base, for I love writing C code and debugging things, and this is how I want to spend my time, looking at little zeros and ones and wondering why they don't do my bidding. Or, you're experts and I'm not, I will give you money, and in exchange for money, you will give me bits. And that will be the firmware, and then it's very clear when it breaks, I gave you money and I can blame you for that. Now this code base is very important because it allows a lot of differentiation between products. So a lot of vendors in the room, when they make a platform, BIOS features are how they differentiate. In the server space, this can be error correction, logging. In the desktop space, if you're making a high-end gaming desktop, people love graphical interfaces. So if you buy an ASRock board or an ASUS board or an MSI board, they have some really cool GUIs in the preboot environment. Because if you're overclocking, you spend a lot of time in the preboot environment, and you have charts and graphs and dials, and that's kind of awesome. It also has resource implications. BIOS vendors here employ hundreds of people. They're very good at what they do. I work in marketing because the people that wrote code were better at it than I was, because I do presentations now. But those resources are experts that you may not have at that company. So if you need a BIOS expert, you can pay them the salary all the time, or you can contract them when required. Again, this is the way when you see a board at retail, most of your firmware is going to come in that fashion. Now there are some exceptions. If you come to the Intel SSG test suite, you're going to see a UEFI development kit. That's where we take a current retail board, something that doesn't have all the scary blue wires and the cap tape on it. All the features work, no smoke has come out of it, and we put the latest firmware from tianocore.org on top of that. And that way you have a stable piece of hardware, but you have the latest UEFI features, and you can get a debug version of the BIOS. If you go and go to the market, I was already in the market, the computer market here, and buy a board, it's not going to have any debug options. They're all turned off for speed and optimization, and because the competitors shouldn't be looking at how you did things. If you want to debug an option ROM or an OS loader, the debug version of the firmware is really, really handy. You attach a serial port connection to the board, and you get a log, and it tells you why things crashed. We were using it just before I came up here to look at issues between two different versions of our BIOS and why one of the cards wasn't working. So that's really good if you do peripheral testing, if you're a driver developer, if you're writing an OS loader. If you're working with Intel as a manufacturer, you're probably going to get a reference BIOS. A reference BIOS is very similar to this, except it's designed for the early version of the board. So this is the board with the scary connectors and debug wires and little LEDs on it that tell you when it crashes. Not a board you would ever ship to a customer. Sometimes if you work with a reference board for a laptop, it's probably 4 times bigger than the laptop we want you to make. That sort of thing. And again, those have a specific version or a specific purpose for testing the reference, testing the silicon. They're used to more exercise the board than they are to provide shipping firmware. So if you had a reference BIOS, you would never want to give that to a customer. It's kind of slow, it has a lot of crazy messages in it, it has options for bits that nobody understands how they work unless they read the documentation, and you don't want the customers to ever touch those bits. So yeah, never let them touch those bits. So if you look at the life cycle of a product from the early silicon from a manufacturer like Intel to the product phase, you go through three distinct phases. One is the reference platform. Again, this is an early test sample. You're probably not going to see many of these out in the world because since they're limited volume, they're very expensive to make. That means that we have all of the debug options. You can do all kinds of wonderful things with the silicon, but they're maybe not the best things to test hardware with. They're not entirely stable. And there's a very limited number, so if you rely on using this for development, you're typically sharing them with a number of engineers at your company. Then someone comes along and makes an actual product design, either from the OEM or ODM side. And this is where you get product substitutions, use a more affordable version of the SPI flash or memory, take off some of the debug connectors, remove all the debug options that slow the BIOS down or present messages to the user that are very confusing. And then you end up with a final customized product. That platform has all of the branding, it has the pretty user experience, it has recovery options, and that's the thing that you end up seeing if you buy a computer in the store. Okay, so this all works. This is great. I paid for part of my house doing this for many years. Why does this change? Why would I want to give any update about this? There are different ways that people develop products now, and there are different factors that require that we don't replace that model, because that model works great. But there are certain customers that want to use a variation of that model, or certain platforms that don't fit a traditional BIOS model. The first, if you're doing something called a symbol derivative. This is if your customer is not doing any innovation in firmware. Everybody in this room understands that we do a very important job in the industry providing very good firmware, very good drivers, and most people don't know what we do. Right? It's a job with very low respect unless you work with people who understand how the industry operates. So if you go up to someone at a party, assuming that you can ever get any time off work to go to a party, let's just pretend we all go to parties, and you tell someone, I write firmware for computers. Really? No, that's not your first line to someone unless you know that they're in the business. Then you spend the rest of the night explaining what you do in firmware, and they get bored and leave, and you're by yourself at a party, which is very bad. So there are a lot of customers when they first start designing a product, they want to understand why firmware is important. And they don't maybe want to differentiate with firmware. If I have my cell phone, right? Cell phone actually does a lot of interesting things in firmware, but most manufacturers don't understand you need those kind of things like recovery options, right? There's a great recovery option in most cell phones. Hopefully nobody ever has to use it. So you may have a customer, their differentiation is entirely based on the product after it boots to the OS. And there's no differentiation in firmware, so they don't understand why they have to go to an outside vendor, or they don't really need to make a large number of changes. And so you want something that you can pass on to them very quickly just so they can ship the product. Second is open hardware. Products like the Raspberry Pi, the Intel Galileo, these are open schematics. Everything is done in Creative Commons or open source license. And so if it's a very inexpensive board and you want people to be able to modify the firmware, going to an outside vendor, probably not good. The vendor won't make any money because no one will want to pay for it because it's open source. And really the purpose of that product is not to make a heavy revenue stream off of the actual hardware. It's to encourage people to do development and use your architecture. It's more of like an outreach program. It keeps people interested in what we do, and hopefully you get more people who understand what firmware is, and when you want to retire, somebody can actually do your job. If you want to take a weekend off, somebody can actually do your job. This would be nice if we had more people like this in the industry. And then there's also, from our standpoint in Intel, a lot of markets we haven't been in traditionally. And most of those people know nothing about firmware. They know they want to build something. They want to build something cool, and hopefully they want to build it with my stuff, because I'm not just an employee, I'm a shareholder. So you want to encourage people very easily to get into the ecosystem. And you need different ways of providing firmware to them, because firmware is a nice thing to have on the board. And honestly, if we didn't do firmware very well, then we wouldn't have the opportunity to run different types of hardware, different operating systems. You couldn't buy a laptop and say, hey, I'm not sure about this Windows thing. Everybody tells me that Linux is cool, and try out all the different Linux versions. We're not going to say which one's best because they're all in the room and they're going to start fighting. So we'll go to the next slide. Okay, so again, why am I telling you? You're like, I want to go back to my room and fix things. Why am I listening to Brian talk about something I probably already know? All right, you understand the existing IA firmware ecosystem if you're here. You probably have a bunch of business cards from AMI Phoenix inside. You have all their numbers programmed into your phone. They're tired of listening to you call when the driver's broken or when the OS doesn't boot. We know how this works. But if you start using these different platforms, you shouldn't be surprised that the firmware support is going to be different. If you go and buy a Minoboard Max for very simple Intel development, the AMI and Phoenix and Insight don't want you to call them when there's problems because they didn't have anything to do with it. Right? So you need to understand where the firmware comes from in these different products. Okay, so I'm going to break this down into 3 new models that you'll see that are in addition to traditional BIOS vendors. One of them fully embraces open source. One of them uses open source with a combination of binary components. And a third one will have binary components that sort of fit together. I don't want to say Lego because that's copyrighted and I'll get sued, but you have pre-built components and they kind of snap together to build a full firmware image. Open source is kind of the easiest one to understand. We do a lot of work in the Internet of Things market. We have an Internet of Things group. I guess we have a thing full of other things. And these are typically fit into the hobby space. So people will compare this a lot to Arduino or Raspberry Pi or Panda board, those types of projects that are very low cost and have almost no secrets about how they're designed. So our Intel Galileo board is an example of this. We make a processor called Quark, which is 400 megahertz single core, reduced instruction set. It's very close to Pentium or 486 design, if anybody is old enough to remember that. I'm old enough to remember that. And anyone who's worked with Intel is going to be surprised, there's no VA required to look at the source code. Yeah, we had never done that before. That's kind of cool. You can get the BIOS writer's guide off of a website. That's kind of, if you worked with Intel as long as I have, that's kind of weird. All the open source references out there, and it's all based on EDK2. The really cool thing about it is it's not very big. It's also a good example of how you do a reduced form factor. Everybody, and if you look at all the security attacks people talk about, they say UEFI is too big. Now what they mean is if you implement everything in the spec, UEFI is too big. But nobody implements everything in the spec on a single system. So the Quark is a nice chipset because it has no video, very low speed, has very few bus interfaces. It uses total in its EDK2 project 11 modules, 11 packages total. 3 of those are Intel and the other 8 are open source. That's pretty small. So you can actually do kind of a demonstration of this is very thin firmware. You don't have to have all of the things present. We also did TinyQuark, which Don Way talked about in the opening presentation. TinyQuark is 64 kilobytes full. That's the whole implementation. That's not just the boot block. And that will boot to Yocto Linux that you can embed into the flash. There's a 4 megabyte flash on the Quark platform. So you can put the entire OS and firmware and be written to a standard and have that in a single image. So that's another good demonstration and another good example of making a thin layer of firmware as opposed to the larger firmware that everybody associates with BIOS and everybody associates with UEFI. So that source is available on our UEFI development site, which is uefidk.com. The second is when you get into open source plus binary components. Now, I love open source. I think it's great. Lawyers, however, don't always love open source. And sometimes you do a very cool and innovative thing in your software or in your firmware, and the company goes, that's great, but you can't just go give that out because that's worth money to us. The biggest example, if anybody here has ever dealt with BIOS, is DDR3 training algorithms. Those are really complicated. I don't know how they work. And a lot of other people don't want them to know how they work either unless they work at my company, so that stuff is typically available only under a non-disclosure agreement. However, if we design an open hardware board and we want people to use that chipset and that platform as a reference. How do I combine that with open source? Well, the answer is that you take the things that are in closed source that require an NDA to look at, and you package them as binaries, and you wrap the open source around that. There's two different ways to do that. One is to do it a little bit more like EDK2, where you take the individual PEIMs or DXEs, build them as binaries, and shove them into an FDF file, and they become part of the binary load of the firmware. So you have a lot of open source, and then occasional points where you go to a specific PEIM or DXE component, and that stuff's closed off. Now, for most people, that's not a problem in open development, because you're talking about things that are fixed on the board. So we'll take the Intel Minnow board as an example, because it's one of the boards I know. That actually is EDK2 plus binary components for memory initialization and some of the CPU initialization. So the memory initialization, all the memory on the Minnow board is soldered to the board. You probably don't have to change that to work with the rest of the platform. That's 1 gig of DDR2 memory. That's okay. You shouldn't have to tweak that unless you're building another board, and then that's a different kind of project. So you can still go in and, say, develop a new EDK2 package and put it into a Minnow board project or a Minnow board Max project and build that without having to change those silicon components. Now the second is a little bit more of a standardized way. We do have a number of customers at Intel that don't actually use a standard firmware. They don't use EDK2, they don't use their traditional UEFI BIOS, they don't even use core boot. They go off and do some crazy bootloader on their own. Most of those are in the embedded or industrial segments. So years ago, we came up with a system called the Firmware Support Package, or FSP. And the FSP is a single binary that we give that says, if you're using this silicon combination, go take this and put it in the middle of your firmware. So your firmware starts here, hands off to FSP. FSP does the magic that you don't have the documents for, and then spits out the other end and says your firmware is now ready to go. So it takes all of the little hidden parts, all the magic Intel bits, and does that for you. Here's the really cool thing about FSP. It's basically PEIMs. We looked at it and said, we have a spec for this. Let's just use it. So all of that stuff is actually EDK2 compliant PEIMs. They just happen to be in this weird container. So it's fairly easy moving forward to integrate that with some EDK2 stuff. Now that means that you're building something that isn't quite the same as a off-the-shelf piece of firmware, and you do have to do a lot of work on it. So it's not like just a magic solution. It does require supporting. But it is an option for doing these open hardware platforms where we want to use a number of Intel components we can't do 100% open source for, and have people that can say, I want a Raspberry Pi, but I want it to be faster and I want it to run the software I already have. Okay, that's probably an Intel product, you can go use this. And there's actually a Minnow board Max in the test suite if you want to see what one of those boards looks like. So again, we do have a project for the Minnow boards that uses this EK2 plus binary kind of combination. In my opinion, it's not the cleanest way to do it because it's very board specific which components get locked up in these containers. So from a debugging exercise, if you want to understand how the boot works, it's not as transparent, but you can still turn on the open source components and do all of that yourself. This is one other point I want to make about this. This last line is really important. The binary components aren't configurable. There's no widgets or pieces in there that say, oh, it's memory configuration. What if I want 2 gig of memory instead of 1 gig? Those kind of binary components are sort of compiled for that specific scenario. They can't really be reconfigured. So it's great for that one particular project, but it's kind of a bad way to support it generically. That's the interesting thing about FSP is since we made it a little bit more based on specifications and also built in the concept it can be reconfigured, there's a tool that allows you to basically tweak the FSP and change some of the parameters that are available for developers. So if you do actually get a project that uses this and you find out that there's a bit set incorrectly, you can go back to the people who did the firmware and say, you might want to fix that. And again, EDK2 can consume this. SEC core hands off to it. FSP produces hobs. Hobs are handoff blocks. that pass information up to DXE, and the rest is reading a very long and not that interesting specification. Okay, now we get into the last part, which is configurable binary components. And again, this is something that we haven't really deployed, but it's something that we're kind of looking at for very specific markets. Again, there are some platforms, like if you look at Internet of Things. The Internet of Things, like we just announced an open source project, Intel's collaborating with Linux Foundation on a standard open source platform for the drone helicopters. So if you want to make your own robot helicopter thing, there's going to be a standard open source distribution for that. Okay, maybe a little creepy, maybe a little cool. Don't know how you feel about robot helicopters flying around. I think it's kind of cool. The firmware in that's probably not going to be terribly complicated. And it's not going to be a lot of difference from one place to the other. You may want to make small changes to it. So somebody's going to spend most of the time playing around with the source for that. They may not want to mess around with the firmware too much. Or if you're building a smaller Internet of Things device, maybe all you want to do is take the reference design and make a couple of tweaks to it. And spending the time on source code isn't your idea of fun. So in that case, we are actually looking at a system that is still based on PEIM and DXE components, but building in some configuration options so that you could present, say, a graphical interface, and someone could say, yeah, I want to take the same thing I used for the reference, I just want to change a couple of bits here, and I just want to change a couple of drop-down options, reconfigure those binaries, and not build it from source, but just put those binaries together in the right piece of firmware. So the Intel example of this is called UBMS. There are, I think, equivalents for this in other architectures where there's a configurable binary that is the main distribution piece. In other words, the main thing that kicks the firmware off and gets it going can be configured through this binary option. Okay, so we've gone over these different options. Which one is the best? Well, that's a great question that doesn't have a clear answer. The reason that your customers or your partners may choose these different options is really going to depend on their business requirements. To be perfectly honest, based on the business requirements and the way that this works, the majority of people are probably still going to be using the BIOS vendors. And it's worked very well for a number of reasons. The BIOS vendors also add a lot of things on that you're never going to see in open source. They have their own patents, their own IP, their own interfaces. So there may be equivalents to some of these options in their toolkits. But really, it doesn't fit every segment. If I made a open source requirement for Internet of Things, that same kind of open source model may not work in server. If I made a configurable binary for making a tablet, it's probably also not going to be a good thing for server. They have widely different business requirements, wide different needs that some of those are going to work great with an enabling partner and some not so much. So there's really 5 questions that determine what kind of enabling model you're going to have. One is this: if the end user needs to modify the firmware. In most cases, the answer is an emphatic no. You do not want them to touch this. So most products are not going to have the need for something like an open source or configurable model. We don't have the idea that somebody releases a commercial notebook and then magically someone can go, that's great, I just want to go over here and put my own firmware on this notebook I bought out of the market. That's probably not going to happen. Second is, how do you protect IP that's in the firmware? If you're doing really cool things for recovery or memory correction or any other kind of stuff like that, a full open source model, probably not the best idea. So maybe you're locking at least part of it up in binary. Will the customers use the firmware to make a derivative design or a derivative product? That's more of a reference design kind of concept. Maybe you're building a reference board for a new interface, and maybe your downstream customer will take that and modify the firmware and make a derivative out of that. So that's where they need some kind of configuration option. Maybe an open source is good, maybe a configurable binary option is good. What level of firmware debugging is required? This is really important. This determines if you go more for an open source level or not, because open source gives you the best firmware debugging capability without involving a lot of lawyers, right? So you've got broader depth of debugging enabled there. But if your target customer isn't going to spend a lot of time debugging the product, that's not really necessary for putting out a lot of source. And which option best fits the platform security needs? This is really important. Security is a big deal for us, right? So if you have a lot of things that, like you're going to build an end-to-end product solution, maybe open source doesn't fit for your firmware because it reveals too many things about how the platform works at a low level. Or maybe open source is great because you're trying to build something that's going to be more part of like a new ecosystem or a new product foundation, and you want more people to adopt it, knowing that the end product made out of that, not the reference design, but the end product generated out of that is going to have secure signed images. But if you're doing a standard product and you're doing things like Secure Boot or TPM, you're probably shipping signed firmware on that platform. Please tell me you're shipping signed firmware on that platform. That makes me feel a lot better if you're signing the firmware, because that makes it harder for someone to come in and exploit it. What have we learned so far? One, Brian can talk 30 minutes about different ways to hand out firmware. Good enough. But we are introducing new options to support UEFI. The models that I've talked about here are all UEFI-centric options that we're using to enable different types of platforms and different types of markets. This is important to people in the room because it may change the relationship if you have a new vendor. How they get firmware changes what tools you have available for debugging or configuration or testing. Some of these incorporate full binary components or configurable binaries or open source in different products. And then by the fact that we're doing more open source at Intel, especially at the firmware level, means if you're doing OS development, then you don't have to call me and say, how do I debug the OS loader? You can just go, I'm going to buy one of these little cheap middle board things and compile the source myself and turn on debug options and figure out how this got messed up, and maybe I can fix it. It does allow developers a few different options for picking the best one that fits their IA product. And then at the end of the day, you might just use the model you have now. If you want to become a firmware expert, we've got some new ways for you to learn how to do it. If you don't, then we have a very good ecosystem for managing those changes, and that works fine too. But this hopefully will keep you prepared so that if you run into one of these new models on a product, you have an understanding of how to deal with it and where that support comes from. And thanks very much for your attention.